another draft physics video and such. So interferometer will be the subject, even though we've been over it before. I'll go over it some more. Curious thing. I mean, there's a lot of so somebody left a comment basically saying, "Look, it's really simple." No, it's not really simple. It's nothing about what's going on in an interferometer. It's really simple. So, so this is a part where they're showing the end signal of a very short interferometer, just a couple inches on either side, and he's adjusting it, this micron kind of way. And all of this doesn't make too much sense to me just because of the distance involved. And we're talking about changing the wavelength of light, which is it's in nanometers is what you measure that wavelength by, and which is 10,000. It's a 10,000th of, or maybe it's well, anyway, it's a lot. Just of a millimeter. So you're talking about a millionth of a millimeter, I think. Very small thing you're trying to detect in terms of a distance. And you're adjusting a mirror, and I'm saying, well, how can you be adjusting a mirror for nanometer distances? It doesn't seem very likely. Well, anyway, so this pattern changes, and they go through these cycles and try to get the pattern back to the way it was. So if you can see there's a couple pieces of tape here to mark where the fringes are. And the idea is you cycle through until you get to the same pattern where the fringes are in the same location. And that means you've gone a half a wavelength. I don't know why exactly that's what it means, but that's what they say it means. So I'll play some of this. Should I guess I had, well, it doesn't matter. So there's no sound. So you can see as you move the mirror, the pattern keeps changing. And so he's going to count the number of cycles: 4, 5, 6, 7. Now the thing I notice is that this isn't a usual two-slit pattern, or even a single slit pattern, or even Newton's ring pattern, because these proportions are way off. I mean, the dark lines are the same size, and the bright lines really change in terms of their size. So that's unreminiscent of an interference pattern, in the sense that these aren't the this isn't what usual interference patterns do. So that's one curious fact that I think needs explanation. Why are the dark lines consistently always the same size, and the bright lines are the ones that change their size? If this is supposed to be caused by interference, there should be an equal. There should be equal. The black lines shouldn't be the same size. They should get smaller, like the bright lines are getting. And well, anyway, so that's curious. So here the pattern matches again at 18, I think, or well, I guess it's some other higher number, 20. Okay. I think in the Michelson thing they went through 60 cycles because they were using whatever it is, a mercury lamp or some sort of elemental lamp that gave a signal when they matched, and so something like that. And they had multicolored fringes, and it's a little more complicated. So anyway, I need an explanation for these bars. These dark bars are looking very much just like dark bars. They're not looking like interference, because they don't do what they should do, which is change their size, and the bright bars are very different in size. So that's just an issue that I think needs explaining. I haven't seen it explained. So anyway, moving on. I think that's all I wanted to use that for. Yeah. So to the drawing and such. So I don't know exactly how to draw this, so I'm just going to give it a shot and we'll see how it goes. So the idea is there's two paths. Okay. Oh man, you could draw a little bit better than that, couldn't you, Gary? All right. So this is the start, let's say, and this is the finish. Just call it next. And the idea is you go to these two paths, and then you go through a bunch of mirrors, and then you go right down, back and forth through the mirrors, and then back. So this one has the same mirrors going this way. Alright, So the argument is that yes, this is really nice for adding distance, but it just doesn't work, is my argument. So the argument is that if you did a by time, and you called the first instance of time when this beam goes through, going through the beam splitter, it's here. So it goes through, this beam goes through and this beam reflects. So this beam goes through it, and then you have to think about how the mirror is moving and the fact that the glass slows the light down, and so it's going to be in the slower glass longer, but we'll just ignore that for right now. So let's just call this a starting point. So that's T0. And so as the light travels, this first mirror is now moving this way as the light's traveling towards it. So that means it's going to be at a different position at T1. And so when light goes back, it's going to start from this position, and now the beam splitter is now going to be moving forward. So when this one leaves at T1, and at T2, when it gets to the beam splitter is going to be closer. So you can say, like, I shouldn't have got this stuff in the way here. So we just, for the sake of it, we'll call this T2 here. 3. All right, so T3 means the mirror is a little closer. So this distance from this arrow, from this further away position, but it's really, it's not further than this one. So this distance is your real distance, this length. So we can just say that's the real length of the first leg. And then this one's going to travel a much shorter length because when it leaves, this mirror is going to be moving, so it's only going to go this shorter distance. And so you could say the length going this way goes this distance, the length going back only goes this distance. There was some other thing to consider here too. Let me just think. I'm forgetting something. So it's even worse than that when you really think about it, in terms of the difference in the distances. But the trick is that this distance, only counts for this distance of the first length. And when you get into the mirrors, that's when this doesn't start to matter anymore. Because as you reflect off this mirror and go to this mirror is moving forward. So this distance ends up being shorter. And then as you're moving this way, this distance ends up going longer. And then this one ends up going shorter. And this one ends up going longer. So in the mirrors, you don't do the same thing you're doing on this first length. So the mirrors, it all cancels out. There's no increase in the distance. And so the only distance that really increased was the first leg and the return trip, because the mirrors, it's just canceled out by the back and forth motion. So you can't make this argument that this leg is much longer than this leg. And you also have to account for the fact that this leg has the same problem in the sense that the mirrors are all angled. And where the light hits on the mirror is going to change as the mirrors move. So as each one of these mirrors move, more and more time passes, and they hit a different angle on the mirror. And this is a shorter distance than, the longer distance than this distance. So if the photon hits the mirror at this angle, at this point, it traveled a longer distance to hit the mirror, and it's, and that'll be complicated when it goes to for its reflection. So it's not as simple as, they want to make it sound, as if you can tell really easily which path is the longer path, and there's nothing complicated about this, and all that crap. Now, and then the idea is they're moving this experiment, in Michelson-Morley, they're turning it, and even though they have it on Mercury, a bed of, floating on Mercury, and they try to take away all the vibrations possible, there's no real way you can move it without making nanometer changes in terms of vibrations and just compressions on the device itself. And it seems pretty impractical to think that you're going to be able to measure this And it's, again, the real distance, it's the only one that's really a longer and shorter path. I mean, there's a longer, more time going this way than time going that way, is this length. And again, you don't know how much of that also is happening in these mirrors. So you don't know if you have a control. So ideally, you would make it on the ground, and you would make it without mirrors. You'd have a straight route, you know, for one length, and a straight route for the other. And then you just watch it throughout the day and see how many of those cycles, those blinking cycles, you went through. But those cycles don't represent an entire wavelength of change, or a half wavelength. Like I said, it was 20 cycles they claimed was a half a wavelength out of phase. And so that's even measuring something finer, which I don't think they could do. So I find it, you know, this is way more complicated than the superficial analysis that's given by most people. So, yeah, so what I want to get to is I do have some of this film, and I don't know if I can really show anything, you know, in this, you know, here. And it's not ideal in the sense that it doesn't have the randomized diffraction lines, but you can see it creates a lot of images. And the question will be is, are those images spaced similar to the spacing of the ringed pattern? But I can do a reflection, which is, so I think I can make a beam splitter out of this, and it'll have a bias in the sense that it won't be it won't create a Newton's ring, but it'll be interesting to see what it does create. So I'll attempt to work on that. And what else do I want to point out? Because, you know, it has a reflective, at 45 degrees it does reflect pretty well, and creates lots of image distortions. Let's see if I can get any good ones to go on the paper. Yeah, so, you know, like I said, it's only going one way. I mean, I could use two pieces and then have them go both ways, but it'd be best to have a randomized one. So I'll have to look into purchasing a more legitimate beam splitter. I think I can get a cheap one for $10, but we'll see. First look anyway. So again, you can sort of see the distance between okay, so you got to go in straight, and so that's the more traditional pattern. And you can see they get wider as they go further away, not narrower, and that's not what you're seeing in the interferometer image. So yeah, I have to work on that. So let's do anything. Well, almost makes me blind. That was a good trick. Creates dots everywhere. Anyway, I have to keep track of what it is. Well, anyway, I have to work on that. So what else do I want to... I really wanted to go into this a little better than I just did. This distance difference. So the difference in the distance means something only in the sense that you're not comparing this beam. I guess I could use red. See if it works. You're not... Oh, it's purple. You're not comparing this distance to this distance in the interferometer. I mean, obviously the two beams you're comparing is this other leg going this way and the leg going this way. So this distance doesn't mean too much. I mean, a change in the distance, if the setup is wrong, it doesn't really matter, because all you're looking to do is get that pattern match. So as the video in the beginning showed, all you're trying to do is match the same pattern, and once you have the pattern match, you know you're on the canceling wavelength, then you're just looking for how how many times it does that blinking out thing. So I guess I'll play that again and then call this less than productive video. But anyway, alright, yeah, so back to this. So what you're really just trying to do is duplicate, count how many of these, I don't know what to call them, where the fringe collapses into the center. And so you're just basically counting how many collapses there are. And that's supposed to tell you, whatever the number is for whatever light you're using, is that number represents a half a wavelength, or a 90-degree shift in wavelength. Apparently, that's what I can glean from this. So, but again, look just how consistent the black lines are and how inconsistent the size of the red lines are, which isn't consistent with traditional wave mechanics and such. So anyway, I don't, like I said, I want to get too deep into this because I think it's I think there's something more complicated going on here, and I don't know if I want to invest too much time in it, but it is kind of important because this is, connected with the gravitational wave thing, and it's connected with arguments that somehow they've proved that light somehow compensates for these differences in length by somehow staying in phase when it should be out of phase or something, as the argument. Somehow light knows the distance is different, when I would argue it can't do that. So anyway, I mean, they're turning it into a relativity experiment somehow, and I don't exactly get how they're doing that, because again, you're not comparing this forward distance against this backward distance. You're comparing the distance, the time it takes the light to go through this pattern against the time it takes the light to go through this pattern. And especially as you turn the experiment, then you're starting to move these mirrors a lot more as they become relevant to, say if you're measuring the Earth's movement going this way. So this is in line with the Earth's movement, this leg. It would be the one creating the longer distances. That's what I sort of meant by the mirror moves, is that the mirror is supposed to be moving with as the Earth moves, as the Earth rotates and also rotates around the sun. But how are you going to measure those tiny differences in a length that short? I mean, you have to have a very long distance for those differences in length to matter, in my opinion. A really long length. Yeah, that's probably enough. I don't know how they have the LIGO thing arranged. If they have one that goes east to west, then they should be able to, if one of the legs goes east to west, then they should be able to do the experiment where they just watch it for a day and see how much it changes in 24 hours. How many cycles it goes through. But anyway, maybe I can think of some other way of doing it. But anyway, that's enough of a video. Yeah, so I'm right at the minute. I'm sort of fascinated by these lines. Have me bugged. it's not diffraction. They're the same size, and they shouldn't be. Well, they should be. The bright spots shouldn't be different than the dark spots, and the fact that they are must mean something. Anyway, yeah, it's enough. So, yeah, that's sort of what I want to point out with the laser, is that when the laser creates these spots, those are essentially representing, because it's not randomized. So those dots are essentially the same as the rings. So that's what a diffraction gradient does. It creates those dots. Oh, I don't have the camera on. Sorry. There. It's a little complicated. Yeah. Have to remember these things. All right. So those dots. So it's just a laser beam shining straight through. There's nothing engineered here. Too bad there's a little bit too much glare, but anyway. So those dots are a lot smaller than what it looks like there. They're kind of blurry. Let's see if I can move back or closer, make them a little less different. Well, anyway, they look a lot more consistent from my perspective, obviously. They're definitely, the center one's brighter, but the point is those would represent the rings, those dots, essentially, mostly, kind of. I can rotate them here, but you know, because randomizing it would have them going all in different directions. But randomizing the spin this way doesn't fix. See, the idea is that they probably have little lines in the mirror, so there's probably some kind of idea. The half-silvered mirror is probably something like this, you know, just a bunch of little whatever, and so there's just as much white space as dark space if it's done correctly. And so and the thing I just showed is just lines going in one direction. So the difference would be is that where the dots would line up for rings wouldn't be the same for this mixed pattern. The mixed pattern would end up making dots that wouldn't necessarily be the same distance, might be the argument. But it might not be off enough to make a difference. See, the point is this is a very small laser beam being shined on there, and the deviation between this location and this location in terms of you're projecting these dots at distance. And so this little difference, this little change in the focus wouldn't create much of a difference in the pattern. So that's sort of the argument. There's not enough difference, so there would tend to be a ring created even by a mixed pattern, but I'm just not sure of that. So parts of this, like, I'm just not comfortable with this. But anyway, questions to be answered, and you know, thought has to be given to that, all that crap. So I don't know if I want to waste too much time on it, but we'll see. Anyway, no, till next time and such.